and it doesn't mean you won't see it in the paper. Now someone's going to say, oh, we use canonical correlations all the time. Probably not, but there must be some people that do. So canonical correlations is faced with the same game as linear discriminant analysis, but best is defined somewhat differently. Canonical correlations does sort of work better when you have more than two groups, sometimes. Sometimes. So it's possible you would see it in a paper. If you do, send me an email and say, hey, guess what? They use canonical correlations. This is probably in a paper written in 1964. Not necessarily. When the bullet says analysis is usually heavy on visuals, that's because the math is super complicated and drawing pictures is sometimes better. Let's see what's coming up. Oh, jet fuel. So this is a real example. I don't know. Jet fuel data. I remember the example coming in and discussing it with Bill Raines and making slides a while ago. So there are different types of jet fuel, and since you have more than two groups, then typically you have more than one discriminant function. So both canonical correlations and discriminant analysis, just like with principal components and partial least squares, you can make more than one discriminant function. So this is why logistic regression oftentimes loses in the multivariate case. You can also do multiple groups in logistic regression. And you end up running multiple logistic regressions. And it doesn't typically work as well as the methods that produce multiple discriminant functions. So logistic regression goes down in popularity as the number of groups increase. Why? Because it doesn't work as well. And so in this case, let's see what we have. We have 4 groups, 90 variables. I wonder what our sample size is. Fisher's approach produces 3 new variables. So this is multiple variables that are good at discrimination, maybe. And you notice down here, there's the discriminant analysis score here, the second score here. So they're like principal component scores, right? They're linear combinations. But these linear combinations are good at discriminating between the groups, and we get a super ideal plot. So here's another plot that you need for your paper. If you can't plot it, they're not going to believe you. You can't just use the method. You've got to have pictures to go along. And methods that produce scores, like discriminant analysis, are really helpful because you can plot them and you can show that. So if we're trying to show that the jet fuels are different, that is a great plot for doing it. Yes, I can do 90 one way. By the way, what's the first thing that would happen? If I'm given 90 variables and 4 fuel types, I'm probably going to do one-way ANOVA 90 times. Because why not? I've got 4 groups. I'm interested in which of these variables are different between the 4 groups. And I can put that in my paper if I want. Or I can, even though I did start that way, doesn't mean I have to end that way. And if discriminant analysis can make a beautiful plot like this, by the way, principal components might be able to make a nice plot like this too, right? So which one's right? There's no right. they're different plots. But there's a reason why we chose this one to put up on the slide, because it says exactly what's going on. It says whatever that fuel type is really different from the other three. I could say that with my 90 one-way ANOVAs probably, but it's not the same as having a plot. So this makes the point that group is really different. These groups are very different from each other too, right? There's a little pile, 3 different piles of them. If I'm going to classify, I'm pretty sure my new points are going to be over here or in one of those groups, because there's not a lot of variability. So how am I going to classify one in the middle? I hope that doesn't happen, right? But it could. Well, that's a new fuel type. Who knows what's going to happen? But the point of making a plot to go along with your analysis is essential. So if my papers about these fuel types are different, starting with the plot, people are inclined to accept your paper. Starting your analysis, well, initially we do 90 one-way ANOVAs, blah, 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 and they're bored. You got to win in the beginning. So, and that's, if that kind of plot's going to help you get people to think that you actually found something in your data, which you did in this case. We found that the fuel types are very different from each other. So if we're trying to classify a new observation, I bet we're going to do pretty well, maybe. So we put an unknown there. Oh boy. How are we going to classify this guy? It's got to be one of those, right? It's probably not the red guy, and it's definitely not the dark blue down there. So what's happening in practice? Plotting the scores in 2 and 3 dimensions. We're making a score here. We're making a score here. We're making a score here. Logistic regression, you don't usually isn't really a score. So, and that's one of the reasons why you wouldn't typically, we analyze the data using logistic regression doesn't generally start with a plot, because although I wonder, there's probably some theoretical work to do to generate a nice, there probably already are some nice logistic regression plots to go with. We like plots in 2 and 3 dimensions. I still don't see papers, only the graphical statistics journals have 3-dimensional plots. It just doesn't happen in one of your papers very often. It should be, and we, as statisticians, we want people to use 3-dimensional plots, but we haven't been able to convince biologists to actually use them in their paper. Doesn't really make sense. A lot of the papers are online. You can pop up a 3-dimensional plot in an online paper. We can embed them in, we can do all sorts of things that are super cool graphically. But we can't actually convince people to use more than 2 dimensions. When we get them to go from 1 dimension to 2, we're happy. So my 90 one-way ANOVAs are a bunch of 1-dimensional things. My 2-dimensional plot is a big step in the right direction. So if we're going to, so canonical correlations is here's Bill's point, this is not a classification rule, but it really is. It can be used that way. It is better at boundaries. Let's see if we put the boundaries on. SAS code, who cares? A bunch of mathematical stuff. By the way, the linear algebra behind Fisher's method is super complicated. Those are the group means. So the way that discriminant analysis is working is we have there are the means of the three groups, and this is the artificial example, obviously. We're going to split up the space using lines. Why are they lines? Well, they're lines because we're doing linear things. Is it a good idea to use lines? Not necessarily. In future slide, we'll talk about making them into curves, which might be better. But so by splitting up the space in some optimal way, anybody in here is going to be classified as group 1. Anyone in here, notice this space is not not circular. It's split up by these lines. Anyone over here, everybody what the heck happens with these guys up here? Yeah, we got a problem with the guys up there. Where are we going to? So what happens if the observation's right here? Then we're going to have to go with group 2 as our guess. So if the observation's up here, then group 1 is a triangular region that